Please welcome to the stage Associate Director for Networking at the U.S. Department of Defense HPC Modernization Program, Air Force Research Laboratory, Ralph McEldowney.
Good afternoon, SC25. Welcome to our invited talk session on national strategies. We have two fantastic talks for you today. First will be a talk on HPC resources in India, and second will be quantum research being conducted in France and the European continent. So with that, I'd like to introduce our first speaker, Sanjay Wandhekar. Sanjay is the head of the Center for Development of Advanced Computing in Pune, India. He spearheads the development of advanced HPC technologies and the establishment of supercomputing facilities across India under the National Supercomputing Mission. To date, 22 high-performance supercomputers have been deployed, and many more are in progress of deployment under his leadership. Sanjay was a core team member in the development of India's first supercomputer between 1990 and 1991. With more than 35 years of experience in designing and managing HPC technologies and systems, he has played a pivotal role in shaping India's supercomputing ecosystem. Please help me welcome to the stage Sanjay Wandhekar.
Good afternoon, all. So first of all, I would like to thank SC25 for giving us opportunity to present our work under National Supercomputing Mission, which is actually aimed at self-reliance in HPC ecosystem. So a little bit about Center for Development of Advanced Computing, we call it C-DAC. We are established in 1988 to build the supercomputers of India. So this is how the C-DAC started. And over the period, we have been working in the various areas of IT and electronics. So started with HPC, now we are working on the quantum computing. We are working on the RISC-V developments also, embedded processors, as well as now we are going to work on the HPC class of processors, as well as strategic electronics, software technologies, including free and open source softwares, health informatics, cyber security, cyber forensic. So all the areas of IT are covered by C-DAC now. So because it's a national institute working in this area. So this is a journey of C-DAC, starting with the first supercomputer, which was developed in 1991, which was based on transputers. So this is about 256 node or 256 number of chips were there in that, and those were actually parallel processing. So previously, you know that it was vector computing era, and now we started with the parallel computing, and we developed all the tools during 1991, and then this is the Param 8000, which was actually built after the technology denial from US for giving us the Craig supercomputer. So the journey started from that. Over the period, we developed various supercomputers based on UltraSpark, Spark 8. Then we have worked on IBM processors. Then we had actually developed a Garuda Grid, which is again a grid computing, where we connected multiple supercomputers across the country. And in 2008 and 2013, we had Intel-based systems. Again, these are developed under this program. And we were actually, in 2013, this supercomputer was, Param UR2 was about 63rd on the top 500 list. After that, we started with the journey of National Supercomputing Mission. In 2016, the government of India supported us on this, and the journey of NSM started in 2015-16. So this program is supported by two ministries, Department of Science and Technology and Ministry of Electronics and Information Technology. This is about 700 million program, and now we are actually, this program is getting over in sometime in March 26. So this program is implemented by C-DAC and Indian Institute of Science. So C-DAC is the main implementing agency, and Indian Institute of Science working in the area of research. So under this mission, there are 4 pillars. One of them is basically building the supercomputing infrastructure within the country, which is basically mainly the capacity building. Again, these are indigenous systems built with a phased manner, starting from assembly of the systems. Then we did the manufacturing of the systems. We actually mandated the OEMs to manufacture the system within the country. Okay. So that is how the ecosystem of manufacturing got developed in the country. Now we are, the current generation systems are designed and manufactured within the country. So we developed various technologies, starting from compute servers, we call it Rudra servers, then high-speed interconnect, Trinetra, which is a 200 gigabit network, system software stack, and this acted like a catalyst for high-end electronic design and manufacturing ecosystem within the country. And now, many of the vendors are actually manufacturing their products within the country, like HP, then Eviden, as well as NVIDIA is building their switches and network cards within the country. So this is, these are the 2 main pillars. First one is basically building the infrastructure. Second one is basically indigenous developments to build the systems. Third major pillar is applications of national importance. So under this program, apart from the users doing their research and using the systems, we have built some few applications which are of national importance, and these are basically ready to use by the end users. So I'll talk about those things in later slides, mainly in the bioinformatics, flood forecasting, urban environments, seismic data processing, forest fire spread modeling, and some of the codes in material science and chemistry. Fourth pillar is basically developing the manpower, which can utilize these systems as well as manage these systems. So here we partnered with academicians and industry partners like Intel, NVIDIA, OpenACC, ANSYS, and so on. So they are actually helping us to train the manpower, and about 26,000 manpower trained at various levels, starting from workshops, hackathons, 6 monthly courses, and so on. So this is the infrastructure is built using our own indigenous technologies. Till now, 37 supercomputers are commissioned with about 40 petaflop of compute power of various sizes, starting from about few hundred teraflop to 3 petaflop. Okay? These are all double precision petaflop configurations. Now 10 more supercomputers are under commissioning now, and another 6 months down the line, we'll have another 60 petaflop of compute power. One of them, largest one, is about 30 petaflop, which will have about 3,000 servers, which are built using our own technology. So this current 37 systems are being used by about 13,000 HPC users across the country from 250 plus institutions. More than 1,500 PhD students are using these systems, 50 plus startups, and about 1,800 publications which are reported by those people. There might be many more. And these systems are currently utilized more than 85%. In HPC, this kind of utilization is very high. So that is where actually over the period this capacity is built by training the people, making them aware of these facilities available, and then over the period this is what is the outcome. And now there's more and more requirements. So that is how actually we build the system, so that instead of building a bigger system, we have actually built smaller systems so that capacity is built across the country. That is what is the idea of doing this. So this is the basically distribution of these supercomputers across the country. You can see all over the country this at various research institutions, academic institutions, this is what is put up. So this is the system which is the, currently operational. We call it Paramrudra. This is based on our own indigenous technologies, starting from these servers are designed within the country by us, and they manufactured also within the country. About 6,000 such servers were actually put up in the systems across the all these systems. So these are very high dense servers. About 64 servers per racks are there, and if you use only the CPU only nodes, then it consumes about 35 kilowatts per rack, and some of them are with the GPU and other thing, it goes to almost 60 plus kilowatt per rack. And all these are liquid cooled servers. You can see this is the system, which is a 3 petaflop system, which is already put up in 3 more places like IIT Bombay, IISc Delhi, and IIT Madras. Apart from that, we have AI infrastructure also, which is built, but this is again, this is a bought-out system. This is based on DGX platform. We have a mix of A100s and H200s, DGX boxes. This is mainly being used for AI-related applications. More than 1,000 plus users and 61 startups are using this. This is of capacity 538 AI petaflop, which is FP16. This was actually 75th in the top 500 in 2023 timelines. There's one interesting application which is got developed under this program. This is a real-time processing of radio telescope at giant meter radio telescope at NCRA, TIFR. And this is facility. This facility is the only radio telescope in the world to find and localize fast transient sources over the full 300 to 1460 megahertz radio spectrum before actually SK is getting installed. So this is one interesting application which is developed where real-time data is coming from the antennas with the 10 gigabit Ethernet, and that is fed to these systems, which uses about 100 A100 GPUs at various stages of this pipeline. The first one is basically a correlator and beamformer, which is again real-time processing this data which is coming from the network, and it is getting it does the forming of 2,000 beams at 1 millisecond time resolution, and the data, the intermediate data is saved into the 2 petabyte storage, and it triggers the next stage whenever there is a transients, and then the next stage starts the time domain search on this data, and that is how things are working. And the last stage is basically doing the imaging and confirmation. So as I told you that these are these systems are based on our own indigenous technologies. So these are the 5 indigenous technologies which are getting developed, and this is again a continuous process. Various versions. We started with cascade-like processor way back. Now we are working on the Granite Rapid. In between, we had the Emerald Rapid kind of process, the servers. Apart from that, our racks are very dense, as you can see in the right side. This is a rack with a centralized power supply, which is on this is the first version of rack, but right now we are using OCP ORV3 racks. And again, these are liquid cooled. You can see these are liquid cooled cores. So these are the servers which are actually getting deployed now. About 1,500 such servers are getting deployed under this mission. First one is very dense. You can see 2 nodes within 1 OU form factor. Again, these are liquid cooled servers. About 64 such servers are put in the one single rack, taking about 64 kilowatt of TDP, and the peak power can go up to 100 plus kilowatt. The second one is actually with GPUs. Each server is taking 4 GPUs. Such 2 servers are there in one chassis. And the same thing is actually put up in the standard form factor, where it can be used apart from your supercomputers. It can be used in the standard data centers, which is having an independent power supply. We also have an AMD-based solution. This is a dual socket 4th and 5th generation AMD. It uses this EPIC series of processors, and it supports 8 MI300 and MI325X platform. Again, this is mainly used for AI-related works. Currently, it is liquid air-cooled. We'll be shortly making it liquid-cooled. We also developed a indigenous HPC interconnect. This is mainly for strategic reason, and currently this is on FPGA base, so that is where you can see that it is working on PCI Gen 3, but still we are able to get 200 gigabit kind of bandwidth, and this is a switchless network. Each card is having 10 links of 200 gigabit, full duplex interfaces, and we can have various topologies starting from Taurus, Dragonfly, and so on. This is already in production, and we have already deployed a 128 node network in our system. And this is giving almost equivalent performance of InfiniBand. This is again low latency, high bandwidth, scalable network, as well as low overhead in terms of CPU. It is the CPU is not involved in the communication as InfiniBand. We are also working on storage. We are using Dios storage. Again, this uses the same Rudra server in the different form factor, and this is also going to be deployed in our future systems based on the requirement. So apart from IT equipments, we are also working on the various technologies. All our data centers are liquid cooled, and we use direct to chip cooling with cold plates, but not all the components are cooled. About 70% is cooling is happening with the liquid cooling, so we are using dry coolers and adiabatic coolers. We also observed that about 10% IT power is saving because of this fan power is actually reduced in this kind of systems. So apart from that saving, we are able to get about PU of 1.2 in the Indian environment, which temperature goes up to 45 degrees. So as I told you that we are working from in the phase manner, starting from assembly of the systems from motherboard onwards to design now for servers now. Now we are actually building a processor also. This is going to be a 96 core processor, which will have a HBM3E on die, on the SoC. About 4 of them, 4 HBM3s will be there. Again, it will have standard PCI Gen 5 and CXL interfaces. DDR5 also is going to be there, about 8 channels. This is being worked out with industry partners. Moschip and Socionext from Japan is working on this platform, and we are actually working with them. We are basically giving them the architectural inputs, and they are developing it further. This is going to be a 2-chiplet processor and based on ARM Neoverse V2 cores. So in summary, the various developments have happened, like Rudra series of servers are being manufactured domestically now under this NSM, and all this is happening with the industry partners like Vividian, Keynes, and Avalon Technologies. Now these people are able to now get the manufacturing orders from other partners like HP and other things. So this is basically a step towards development of indigenous ecosystem for the server market, not only in HPC, but in the cloud market. So this also acts like a strategic requirement for trusted and secure server infrastructure. So next generation Rudra servers are now getting developed by the industry partners. Now, not only C-DAC is doing it, now industry partners are doing it. So that is how the ecosystem is getting built in the country. So as I told you that we are having racks with the density up to 65 kilowatt, current means the whatever deployed systems, and now new systems which are getting deployed now currently, our rack density is going to up to 100 to 120 kilowatt per rack. So this is another thing which we developed, that is mainly the HPC system software stack. This is based on completely open source, but wherever there are tools which are not available, we have developed internal tools. So we have various tools like C-Chakshu, which is a central portal where we can actually manage all the systems across the country from central location. We can create the users, accounting, billing, everything is done on the system. Then again, the ticketing system is there, so which is now handling about more than 13,000 users. And it also does the centralized monitoring of all the systems. So in all these open source tools, we are actually contributing also. We are member of HPSF as well as ADAC. So on the earlier slide was on the system software. We also support the users on the all the application stack also. So there are so many open source applications. Now every user need not be actually compiling and basically linking the applications on these systems. So what we do is we give ready to use applications to the end users. And again, you can see this list of applications in various areas, bioinformatics to disaster management, weather, and so on. So we give the ready to use application to the user so they can start using from day one. They don't have to worry about the compilation and so on, which is basically optimized for this architecture of the system. Then all the other tools, development tools, including programming models, everything is again part of the systems in the stack. We also give tools for AI, ML, DL technologies. Again, this is a mix. Within the same environment, you get all these tools available to the users so that they can have both HPC as well as AI environments in the single system. So as I told you that we have developed various applications across various domains so that the end users can use straight away without understanding what is the background compute is being used. So this is again one development which has happened. We call it an NSM platform for genomics and drug discovery. So the users like hospitals, research labs who are not knowing about the computing, they can start using these tools from day one, including the pharmaceutical industry and agriculture sectors. So these tools and workflows for drug discovery, drug repurposing, and genomics are ready to use and is developed by national consortia of not only C-DAC, but various academic institutions and research institutions across the country. So this is one very good example so that the end users can start using this from day one, the complete workflow and tools without any issues. So we also have a small system where we touch these tools and then release it to the other systems. So these are some of the products and solutions in various areas of bioinformatics. Some of them is put here actually, like next generation sequence and analytics workbench. Then we have a tool for parallel biomolecular visualization and analytics, as well as cloud and big data analytics based service for simulation trajectories. And there are so many other tools which are there. All these tools are put on integrated computing environment. We call it ICE Cloud, so that users can straight away use these tools in some kind of container way, as well as they can share the data in secure way. Because in the bioinformatics area, that is very important because data has to be secure and only the access should be given only to the corresponding users. Second application is on the seismic data processing for oil and gas exploration. This is again a very efficient RTM software for high resolution 2D and 3D seismic imaging for oil exploration. Already this is getting explored by this ONGC and Oil India with their own data, and very good results are coming out, so that the dependence on the commercial software is going to be reduced with this development. Third application is related to early warning system for flood prediction. This again, as I told you that all these applications are end to end, so end user can straight away use with GUI and other things. He can just put in, give the data, and then application will run. It will use backend HPC system without user knowing about it. So this is again a application which is developed for accurate flood prediction, which is going to be deployed across India's river basins. So we already deployed this proof of concept, and this is running in last 3 years now, because you know that in India we have monsoon season, when because of now climate change we are seeing a lot of floods are coming across the country. So this is going to be very useful. So this tool is giving about 2 days flood forecast, which actually takes care of what is the weather there and what kind of rainfall is going to be put and what kind of terrain is there, all that is taken care, and we get village level inundation maps and real time water level information using this tool. You can see this GUI is there, so that the authorities can take appropriate decision and take action. This is now going to get deployed across various rivers across the country, and we expect that more than exaflop of compute power will going to be required for this kind of requirement within the country. So fourth application is related to urban weather, flood and air quality forecasting system. Again, this is a ready to use application for municipal corporations. They can actually take actions mainly on the air quality related issues and flash floods within the city using this application. This is another application we have developed, which is a wildfire forecasting and monitoring system. This provides forecast up to next 48 hours using WRF S-Fire model. Again, this is again ready to use application which gives proximity based SMS alerts to sensitize the registered users around the potential fire affected areas. This was recently used in our northeast area when there the fire was there in the forest, and they could actually contain the fire because we were giving real time information to them which area, which direction the fire is spreading, and they could actually isolate the other area and then contain the fire, which gives again displays in GIS format, which is very useful for carrying out near real time decision making. So with this NSM now, where we, as I showed you, that we have developed infrastructure, we have developed manpower, now the capacity is built. Now we need to actually build the capabilities for the next level, where we'll be developing various new applications. So we are proposing next mission, we call it NSM 2.0, under which again we'll be continuing our journey in the indigenous development, where we will be developing processors, GPUs based on RISC-V processor, RISC-V architecture, and GPU also based on RISC-V, and the continuation of next generation Rudra series of servers, networks, stack, software stack, which can support scaling to the exascale. Storage, the new thing which is going to come up is secure grid for moving data across the multiple systems, as well as between the institutions to the system. So this secure grid is also coming up now in the next mission. So this is our roadmap under NSM 2.0. Starting with in 2027, we are planning to have 200 petaflop of system. Again, this is a double precision petaflop. And in 29, we'll be having 500 petaflop of compute power. And in 31, we'll be actually coming out with 1 exaflop of system. We are going in steps. As I told you, that technology get absolute. So if I build 1 petaflop now itself and users are not ready, over the period it is going to get absolute. The hardware is going to absolute. So we are actually going to use the latest technologies in each of these so that users are ready for usage of these systems. So that is how we are actually planning our next mission also, where newer applications will be taken up which requires exascale compute power. And the current applications also will be scaled depending on the requirements to the next level. Thank you very much. So we are at booth 6629 at SC25. Please visit us. We can explain more about various applications. Thank you very much.
So thank you, Sanjay. Are there any questions? If there are questions, please come forward to the microphones that are here in the front row. If there are any questions for remote participants, please enter them in the digital experience. Oh, we have a question over here.
Hi. Thank you very much for the nice talk. I'm Aditya from Oak Ridge National Lab. You talked a lot about double precision petaflops. At C-DAC, are you looking at mixed precision applications? How do you think about being able to use mixed precision for some of the applications that you showed?
Yeah, I think that area is coming up because you know that GPU is now they are reducing the 64-bit precision data, means compute power. Now that is where I think we need to move to mixed precision. Definitely, I think we have started working on that, and we are actually collaborating under ADAC with various institutions. So ORNL is one of them, so you are discussing with them how to actually port these newer applications on with the mixed precision support. Thank you.
We have another question here.
This is Pradeep from KLA. Very interesting, Sanjay. Nice to see. I run a research lab in India. It's nice to see C-DAC doing this. So can you comment a little bit on the NSM 2.0 mission about what GPUs are being used in that Param next generation petaflop 500 and the 1 exaflop system? So
we, as I told you, that we are developing our own technologies, but that will take some time. So meanwhile, we'll be using the latest generation GPUs from the industry. So we have, you know, that AMD and NVIDIA. These are the two major candidates. And if somebody else comes, we'll look into that at those time frame, definitely.
Okay, so it's not yet decided which one it would be.
Yes, yes. But our systems will be compatible with multiple vendors so that we have competitiveness.
Okay, thank you.
I have a question for you, Sanjay.
Yeah.
Does India have a national research and education or national research and engineering network that connects the supercomputing centers that are all over the country together?
Yeah. So we have a national knowledge network. We call it NKN, and all these research institutions across the country are connected. So depending on the institute, they are having currently 10 gigabit to 100 gigabit network. And now we are actually putting, as I showed you, there is going to be grid which is going to be created for our NSM 2.0, which is going to go up to 400 gigabit across some of the institutions, not all of them.
Mm-hmm. That's great. Are there other questions? Anything online? I don't see anything online. Last chance? Okay, well, let's thank our speaker, Sanjay, for a great talk on the HPC resources in India.
Thank you. Thank you. Thank you. Nice meeting you.
I believe we'll hold until 4:15 local time before we start the next presentation. Thanks.
Thank you.
Welcome back. Our second talk this afternoon in the National Strategy session is one on quantum research and its intersection with HPC and AI. Our speaker will be Sabine Mehr. Sabine is currently the Chief Quantum Projects Officer at GENCI in France. In this role, she is involved in the development of the France Hybrid HPC Quantum Initiative, HQI, which is also in collaboration with the CEA, INRA, Eviden, and many other partners. She is also involved in the European HPC Quantum Simulator and Euro-France projects, which aim to couple supercomputing with various quantum computing technologies. Sabine is also the coordinator of the Euro-Q HPC integration project, which federates HPC and quantum computing integration across 6 supercomputing centers in Europe. Please help me welcome Sabine Mehr to the stage.
Hi everyone, so I'm very happy to be here. So as was said, my name is Sabine Mehr, so I work mostly on quantum projects at GENCI, but I will try to cover a broader scope today to present our public infrastructure in France and how it really serves industrial competitiveness and innovation. So that's my objective in this talk today. And of course, so we do that in France, but we do that also in connection with a much broader ecosystem that involves Europe, but also international players, as you will see. So first, the aim is really to explain how the public infrastructure in France works, how we do the public procurement for national HPC clusters, and I will try to explain the role of GENCI, the structure, and why we needed to have such an HPC agency in France. So in order to explain why we needed GENCI, I will talk a bit more about how it worked before the creation of this agency. So GENCI was created in 2007, so prior 2007, all large public research organizations in France, they used to do their own large HPC clusters procurement. So in order to do that, they had limited budget, and they did not, so they tailored the procurement to the specific needs of their own users, user communities, and they did not harmonize these procurements between the large research organizations. These led to a national underinvestment in HPC resources. And so the idea was to try to mutualize as much as possible these public procurement for large HPC infrastructures. Another impact of the way it worked prior to 2007 was that the research scientists, they did not access state-of-the-art HPC technologies, and some of them had to go abroad to use other HPC capabilities, and some of them even saw their papers refused in journals and conferences because they weren't using state-of-the-art technologies. So that was a problem both for HPC centers, for research organizations, and really for end users of HPC systems. So that's why around 2007, there was like a statement that we needed to create a national HPC agency to have a coherent infrastructure strategy at the national level, and to also have the required budget to implement this national strategy. So that was the creation of GENCI. So the main stakeholders who had to reflect on such a strategy are the Ministry of Higher Education and Research from France, and the large research organizations that are CEA, CNRS, the French universities, and INRIA. So what was needed, and so they had to agree on what was needed, was that they had to mutualize their infrastructure budget to acquire larger state-of-the-art computing capabilities. They had also to mandate this French HPC agency to coordinate this national supercomputing infrastructure. They also wanted GENCI to perform and coordinate a centralized technological watch and to provide access to innovative devices, to prototypes for the user communities. And so that was at the national level, but we also needed, in France, to show a united front towards European organizations, such as PRACE back in the days, and now Euro-HPC joint undertaking. So these were the main needs that were seen by these stakeholders. And so for the creation of this national HPC agency, these stakeholders became our associates at GENCI with various levels of involvement. And they also had to define the missions of this agency based on the needs that were previously identified. So the first mission that we have at GENCI is that we have to rely on the 3 national supercomputing centers in France that are TGCC, the computing center from CEA, IDRIS, the one from CNRS, and in the south of France, you have the supercomputing center of the French universities, which is called CINES. So these 3 structures, they work with GENCI to implement the national infrastructure strategies. So initially in HPC, but as you will see, this technological perimeter has evolved quite a lot because it now includes AI and also quantum computing for open research. So our end users, they can access the systems for free to perform open research, and this is really the core of our missions. GENCI was also, so the second mission of GENCI is also to support the creation of an integrated ecosystem at various levels. So we interface with labs, regional centers, national supercomputing centers and national ecosystems, and also at the European level. So we try to federate all of these levels and all of these ecosystems. We are also mandated to promote the use of scientific computing across a wide spectrum of communities. So this is actually a large amount of the time that we spend every day trying to attract new user communities to our HPC, AI, and quantum capabilities. And as previously mentioned, when we identified what was needed, GENCI was mandated to represent the French ecosystems amongst European organizations. So as an example, Stéphane Requena, who is our CTO, is the chair of the INFRAG, so it's the Infrastructure Advisory Group of Euro-HPC Joint Undertaking. This is an example of how GENCI contributes to these European bodies. So who is actually GENCI? So when it was decided to create a national HPC agency, the choice was made to have a private structure that would be able to engage budgets that are actually larger than the annual income of the structure. So that's also for agility purposes. We are 21 full-time employees, so it's a very small structure. Everyone, or almost everyone, is on the picture. You find a broad diversity of profiles. So as we perform large HPC capabilities procurements, we have a very strong legal team that are very versed in these kinds of procedures. They also know how to work on complex European and international projects. We have an administrative and financial team who is also very well acquainted with this complexity. We have an operations team that works on the interface between end users and also HPC centers, the allocation of time on our systems. They also contribute quite a lot to the promotion of the use of this public infrastructure towards end users. And last but not least, we have the technical team with the project managers, such as myself, but we are a broad team working on HPC, HPDA, exascale, AI, and quantum now. So we all work on these various projects that are increasingly complex. But so you see the 21 people here, but obviously, in order to perform all of these missions, we rely very heavily on the teams in the national supercomputing centers of our associates. So obviously, when you see GENCI, you will see these people. But as a whole, we are about 150 people working on all of these projects. And we have a very good complementarity of skills also with supercomputing centers. So as I mentioned previously, the technical perimeter of GENCI has evolved quite a lot. So initially, in 2007, when we were created, the aim was to mutualize the HPC capabilities and procurements and to create an HPC public infrastructure at the national level. But with the AI for Humanity plan launched in 2018, we also procured the GENCI supercomputer that is aimed at addressing the convergence between HPC and AI. That is a very popular system, actually. And you can see it here at the center of the screen. And we also now have an AI factory in France that will strengthen even this converged HPC and AI ecosystem. And since 2020, we have been also involved with quantum computing, first with a Paris region co-funding scheme that I will present later on, but in a more formal way. Since the launch of the French National Quantum Strategy in 2021, we have been mandated in the context of the France Hybrid HPC Quantum Initiative, short, it's HQI, to procure QPUs, to work on user support, and also to work on dissemination around the use of hybrid HPC quantum devices. So as previously mentioned, the access modalities for all of these systems is that they are free of charge for French and soon for European devices, academic and industrial players to perform open research. So it's research that leads to publication of results in archives. Yeah. And so this is an overview of the systems that are now included in this public national infrastructure. So at the left of the screen, you see the systems that are being hosted by CEA, so one of our associates, at TGCC. So now we have the Joliot-Curie supercomputer, which is the host system for the QPUs that are being acquired in the context of HQI. So this is really the core of this hybrid HPC quantum infrastructure. And so the woman that you see right next to the Joliot-Curie supercomputer is Alice Rocoq. It's the second European exascale system that is being procured by EuroHPC, and actually we've received some good news and published some good news yesterday about it. And so when Alice Rocoq arrives at TGCC, the coupling between the QPUs and Joliot-Curie, so the coupling will be deported to Alice Rocoq to have an exascale system with hybridization with quantum devices. The system at the center of the screen is GENCI 4. So it's the fourth extension, well, the third extension of the GENCI system. It's being hosted at CNRS Supercomputing Center called IDRIS. That's also in the Paris region. And so it was the first French converged HPC and AI system, funded by the AI for Humanity plan. So it brings some sovereign computing facilities, but also services to AI research communities, and has more than 3,800 NVIDIA GPUs in 2025, so since also the addition of the latest extension. And at the right of the screen, you see the machine that is called Adastra, which is hosted by the French universities at a center called CINES, so that's in the south of France, in Montpellier. And it exposes AMD architectures, so both CPUs and GPUs. And it's also used for HPC and AI. So we have a diversity of architectures that are being exposed in this public infrastructure. And actually, we have been quite successful in AI because we received, more than 1,400 projects in AI have run on our systems in 2024. And this relies on key success factors, such as the GPUs that we exposed, the user support that was adapted, and the specific access modes that were initiated for the benefit of AI communities. And as I previously mentioned, we are a very European player, so more and more, increasingly. On the HPC side, because we are the hosting entity for the second European exascale supercomputer acquired by EuroHPC. We also now have an AI factory. We were selected by EuroHPC to have a one-stop shop for tailored services in AI that cover the full AI landscape. This has been kicked off on November the 5th, so it's quite recent, and it's launched now. And we are now hosting two quantum devices, European quantum devices, at TGCC. The first one is a neutral atom-based system called Ruby that's been inaugurated on November the 13th, a very busy month. And we have a second system that is a photonic one, and that is called Lucy, provided by Quandela, that's being currently installed. And so the latest news, obviously, that was out yesterday is that Eviden was selected to provide Alice Recoq, which will be our exascale system hosted at TGCC with AMD and Cypel technologies. And I urge you to go check out the video that was made by Eviden to present the system. It's very nice, very luxury-oriented. So you can find it using this QR code. So having the right infrastructure is important. Having the right budget, having also a dynamic to mutualize, to coordinate how this public infrastructure is being exposed, it's important. But we wouldn't be successful with it if we didn't provide the right level of user support around this infrastructure. So today we have a very, very broad diversity of users, either in the public sector on academic research, with various ministries using quite extensively our capabilities in various domains. So we find Mehr, Mehr in the aerospace domain in some, DGA also in the military section. But we also have a very broad diversity of private and industrial players of various sizes using our system. So amongst others, in the startup section, you can find Mistral AI and Hugging Face, which are quite popular at the moment. But all of these players are using our systems. You also have large industrial companies such as Orange, Renault, or Enedis. And so all of these end users, they require a certain level of support in order to be able to use our system in an efficient way. And that's why we have great support teams in the supercomputing centers. So this is not handled by GENCI. This really relies on the teams that are at the HPC centers level. They have very well-known procedures to be contacted for HPC users. Now for AI users, and further on for hybrid HPC quantum computing platform users. And they have very good reputations, which really supports the success of this national public infrastructure. An example of what has been done to make sure that we served the communities right in the support section was the creation of a specific support team for AI communities at IDRIS, so the CNRS HPC Center. We now have 24 people devoted to supporting HPC and AI communities. We also made some adjustments for the access tracks for our AI and HPC and AI devices. There is specific fast track access, which only takes days because it doesn't require peer review. It only requires the agreement of the director of the center, so it only takes days. We also provide a new skill set within this support team, dedicated support team. And we also deployed specific software services that we didn't necessarily have for the HPC communities, like specific container types and Jupyter notebooks as well. And it's been successful, as previously mentioned, because we have more than 1,400 AI projects running on our systems in 2024. And it's the most sought public system of that type in Europe. And this, in terms of infrastructure, this motivated the acquisition of new extensions of the GENCI supercomputer, like the GENCI 4 that was inaugurated this year, as well as the Dahlia, Dahlia, which is an NVL 72 system for academia, which will be used for inference in AI for science. And so we have an announcement also on that, so if you want to check out, use the QR code. So we adapted our procedures and the teams for the needs of AI communities, but obviously quantum computing is again another paradigm. It's fairly new and it requires some efforts from end users to adapt. So we are in the process of creating an HPC QC high-level support team dedicated to these communities with a double-track approach. So we want to be able to support the people who are using these kind of devices for the first time, who don't really know how it works, what they want to do with it. So we have this kind of first approach support. And we also want to provide advanced R&D support for people who have use cases that they know or that they think might be accelerated using quantum computing. And so we will also provide expertise for these communities. And this HLST will be integrated in a Europe-wide team through the EuroQ HPC integration project that federates the integration of all 6 hosting entities of the Euro HPC quantum computers. And so what we also saw is that we have talents in the various regions in France. As you know, we are a very centralized country. But in the various regions, we also saw that there are communities that can contribute to these national efforts around hybridization of HPC and quantum. So we launched the Les Maisons du Quantique, Houses of Quantum Network, to federate the local ecosystems around hybrid HPC-QC, to disseminate around hybrid quantum computing, and to promote the excellence of our French research communities at a national and international levels. And we selected 5 consortia. One of them is based in the Paris region, in 3 different sites. One of them is in the east, around Strasbourg, Troyes, and Reims, with various types of skills, including also the Romeo Mesocenter. One of them is in Nouvelle-Aquitaine, so around the Bordeaux hub. We have also a Maison du Quantique in Occitanie, around Montpellier and Toulouse, and another one in the Alps, in the French Alps, based in Grenoble. So adapting how we support our end users is critical, and this is how men and women working in the HPC centers, the national HPC centers, have a critical mission. And we also needed to build connections with other infrastructure providers, with other types of communities, to make sure that we created an efficient continuum of this public infrastructure for various use cases of high-performance computing and advanced technologies. So this is what we are doing by creating a public-private continuum, because our infrastructure is dedicated to open research, as I mentioned. So the good thing is that users, they can access it for free, and they can access state-of-the-art public infrastructure and services. But sometimes they don't want to do open research, or they need to do confidential research or even business using these capabilities. And in this regards, we also need to be able to guide them towards the right private infrastructure that match the needs that they might have. So our role is also to forge the right partnerships to help them navigate through these different use modalities of this infrastructure. So examples of how we are building this public-private continuum is the partnership that we have with the public cloud provider Scaleway, the sovereign French provider, with which we signed an MOU in 2025 along with CNRS to work on interoperability of our infrastructure, possibility of bursting. And with CNRS are also launching a joint laboratory to work on AI together. We also are partnering with another French cloud provider that is called OVH Cloud, that supports us quite extensively in the ecosystem initiatives that we have around quantum computing, because they are sponsoring our quantum village at Vivatech. They have been for a while. We are working together on a project that is called Cluster, along with Eviden, to really build these bridges between public and public infrastructure and private cloud capabilities. To have something that is a bit seamless. And we're also working within the framework of the National Quantum Strategy on the Aquila project to provide access to a broad diversity of quantum technologies to end users to build some collaboration projects on use cases. And building bridges is also building bridges with even other types of public uses of these infrastructures. So we've signed an MOU in 2023 with the innovation agency of the French Ministry of Defense, which covers HPC, AI, and also quantum computing. So the aim is for us to provide them access to our computing resources for dual uses. We're also working together on joint acquisition of HPC, AI, and quantum systems. So that's the example of the Dahlia system that I mentioned for AI, which was co-funded by this ministry. Proxima, which is a program that is led by the defense in France to work on, to support the technological maturation of some players towards FTQC fault-tolerant quantum computing. We work to organize joint conferences and hackathons. We also share expertise to evaluate technologies, national technologies. So that's a very, I'd say, a very live partnership. And we also build bridges when we do these national procurements, because we work in a very specific way with the vendors, actually. So we are not just any customer. We are like the public customer. So we are a very demanding customer, I'd say. But we also collaborate quite extensively with them. We tend to provide feedback. We want to grow together. These are not just acquisitions. These are projects. We organize workshops. We really work with them to provide as much feedback as possible on the technologies. And this leads us to have a very steep collective learning curve thanks to these public national infrastructure. So this has really enabled very successful projects with which we are associated. The first one is obviously I'm very much involved in this one because this is the first acquisition for quantum computing that we made, leveraging a European project called HPCQS, which led to the acquisition of 2 systems, one by GENCI and one by Jülich in Germany, from the technological provider Pascal, the French company. This was their first delivery ever of systems outside of their own lab. So it was a very rich experience. It allowed them to really industrialize their processes and the product. On our side and on TGCC side, on CES side, there was a huge adaptation also of the hosting site. And I think that the teams at TGCC, they learned also a lot from this experience. And this exposes Pascal's technology to a broad user base also. And so this is, I'd say, an illustration of how, for us, these are specific acquisition, because the risk is really supported by this public infrastructure. We bet on these new technologies. And this led to a very successful project because the system, well, in France, Ruby was inaugurated on November the 13th, along with this twin device, Jade, at GSC. So you can see the teams in front of the system. Another illustration of a huge success that we've had, but on the use case side. So as I mentioned, the first initiative that had GENCI involved with quantum computing was the Paris region co-funding scheme called the Quantum Pack. So the rules of the game is that as early as 2020, the Paris region, they put money on the table to make sure that the quantum experts, the quantum startups on their territory could access collaborations with huge industry players or with industry players that also had R&D teams in the Paris region. And so they co-funded the exploration, not the costs of the industry players, but the costs of the quantum experts. So only the startups and the labs could receive funding, but this de-risked the investment for these first collaborations for the industrial players. And this led, well, the aim was to lead to skill development for the industrial companies and to help them better understand the stakes of using quantum computing on their use cases. And this was also to enhance the attractivity of the Paris region on these specific technologies. And this was quite successful, as I mentioned, because since 2020, we've had 18 projects voted and funded and co-funded that involve 14 end-user companies and a lot of quantum startups that I think that you might recognize. And this is a leading initiative worldwide. So this really was a striking initiative from the Paris region there. And GENCI, at GENCI, our role, and we were joined later on by Systematic and Teratech, was to help create the match between the quantum experts and the industrial players, as we have this, well, we are a part of this computing ecosystem, so we're a well-known player, so it was fairly easy for us to identify which would be good collaborations. And a few illustrations of the impact that this has had. One of these projects actually illustrates the enhanced attractivity of the Paris region on quantum computing, because Multiverse Computing, which is a Spanish company, and IQM, which is a Finnish company, they were also attracted by this co-funding scheme to set up offices in the Paris region. This was not the only lever that was used, but this was part of the deal. And also for Allianz, the German insurance company, they also, it fostered the initiation of an R&D team dedicated to quantum computing in the Paris region to work on this specific project with the two quantum startups. This also led to a lot of interest from the defense industry, which is quite powerful, as you may know, in France. So you see here some projects led by industrial players, very well known, like Thales, MBDA, Airbus, Naval Group, Dassault also, and Safran, who worked with quantum startups like Pascal, Candela, Alice and Bob, and C-12, but also with labs like ONERA, the French aerospace agency, INRIA, the System-X lab, and the ENSTA school, on a broad diversity of projects ranging from the optimization of industrial processes to solving PDs using quantum devices, the optimization of drone traffic in urban areas, and also some CFD studies. And the idea is to initiate collaborations, successful collaborations. So we have had very striking examples of players who started working on quantum computing leveraging these collaborations. This is the case for EDF, who is now very active in this field. They have two collaborations co-funded by the Quantum Pack, one with Pascal, and the other one with WeLink on distributed quantum computing, which is a very innovative field. And there was also a renewed partnership within this co-funding scheme between Air Liquide and C-12. So they have two projects together on different use cases. So I think this scheme really reached the expectations of the Paris region and of the different stakeholders. We've also had, as mentioned, we have a lot of AI projects. We've had some very, I'd say, successful and very visible ones, such as the one with Hugging Face. So they trained their model, the first full open source LLM in 2022, during 117 days on 384 GPUs using GENCI, so the system hosted at IDRIS. And they actually received a prize for that from the HPC Wires readers and writers for the best HPC collaboration in 2022. And we also have AI for science projects in material science in 2024 with training the MACE MPO model with a 300 million element data set using H100 GPUs of GENCI to reach unprecedented time and length scales. And in more traditional HPC projects, which are also quite striking and show how this public infrastructure really serves industrial competitiveness, is the project called Fullest, which led to the world's first ever full engine combustion model, which ran for 3 weeks on 3,000 cores in Joliot-Curie. So this is led by Surfax Safran, notably. So you can see some visualizations of this project. It's very impressive. And we also have other projects like the various portings of the Gisela X code, which run on Jeu Curie for 20 days on 12,000 cores. Nice visualization here too. It's very important for the safety of the design of the next fusion generator, like the ITER prototype that is currently being built in the south of France. And this code was also adapted and ported using a collaboration with HP and Eolen in the frame of the Adastra Progress contract at CINES, so on another system, very successfully. So this shows the broad diversity of very successful projects that are being enabled by this public infrastructure. In conclusion, in a context where you have this acceleration of private investment in AI, the huge requirements of these investments also in quantum computing companies, we see that national public infrastructures, they really keep their mission, which is very specific. We take on the risk of these early investments. That's very, I'd say, visible for QPUs. We work on sovereignty projects. We also establish the link between fundamental and applied research and business, building this continuum between open and confidential research as well. We also allow experimentation on dual use cases, and we foster skills development. So GENCI's role in France and in Europe has remains central to supporting this innovation and industrial competitiveness, and we are contributing to similar dynamics through collaborations at a European level and international levels. Thank you very much, and don't hesitate to reach out.
Thank you, Sabine. That was great. Are there any questions? Please come forward to the microphones in the front of the room. There's one in each of the 3 aisles. And if you have any questions, remote listeners, please ask them in the digital experience. Yes, go ahead.
Hi. So this all sounds very impressive. The very structured, very impressive approach. I'm just kind of curious. It sounds almost too good to be true. What have been kind of the downsides, or what has been some of the limitations to be able to build up an ecosystem like this?
Well, I'd say what is tricky sometimes maybe is that we are relying on different organizations that might have different constraints. So GENCI is not CEA, neither CNRS, neither French universities. So we really need to work continuously on the partnership with these different organizations that actually control our missions. So not always easy, but it's a human adventure, and I think it's working quite well so far.
Also, thank you for this nice presentation. You mentioned the AI factory, and you know the next step are the gigafactories. Do you know if there are any plans in France for a gigafactory?
Well, I know there are. I wouldn't be able to comment too much on that, but I know that definitely this is an adventure that we will be part of.
Other questions? I'll ask you one, Sabine. It's very impressive the interaction GENCI has with the quantum computing industry in France and the startups especially. Is GENCI also involved in any workforce development activities with French universities in the quantum space?
So this is not directly our core mission, but within the framework of the National Quantum Strategy, we interact also a lot with the French universities that have such a program. So we act as an enabler for hackathons, for the organization of training sessions on the systems that we expose, on the environment that we expose. And obviously, every time that we work with these providers, we tend to organize training sessions for industry, for academia, to make sure that end users, they are able to get educated on how to use the systems that we expose.
That's great. Any other questions? Let me see if there's any online. I don't see any online. Last chance. All right, well, let's thank our speaker, Sabine, for a great talk. Thank you. Please join us tomorrow tomorrow morning. We have 4 additional invited talks. We have a session at 8:30 on applications and a session at 10:30 on big data. So thank you, and we'll see you tomorrow morning.